Hello friends, good evening all. Myself Sriram, working in AS Engineering Academy since 2014. Here I am teaching some subjects like digital electronics, analog electronics, basic electronics for public sectors, especially for SSC JE, RRB JE and GENCO students, right? And microprocessors, microcontrollers and embedded systems. See, today's session is for RRB JE electrical preparation strategy. Strictly speaking, the main intention of this course is to revise the entire subject through the questions. So, I am going to cover the relevant topics and some of the basic information and key points and terminology of every topic through a specific question. I have selected some simple questions to some typical level questions, right? And I will also explain the syllabus of basic electronics and its weightage in this paper, right? And meanwhile, if you have any doubts, you can please chat with the chat box, right? You can send the messages, I will give you the reply, right guys? And see, and this is some information for you, not only for the RRB JE, even for GATE, ESE and other public sector examinations also. We will have live sessions and already completed preparation strategy videos are available in YouTube behalf of ACE Academy. Definitely, if you go through them, you can get some extra information. At least one point is sufficient to give you 1 mark, right? So, definitely these videos will give you some important information and some content, you can go through them, right guys? Coming to our session, so our session was actually started, right, RRB JE concept revision through questions started from 7th April. You can verify all other subjects also, right? And today's subject is today's and tomorrow's, right, subject or basic electronics part 1 and part 2. So, actually the basic electronics syllabus, if you see, it is not in elaborated fashion. Some precise manner the syllabus and subtopics are given like this. And surprisingly, you can find the same topics in SSC JE syllabus also. So, basic electronics, electrical paper, for the electrical paper, the topics are almost same from RRB JE and SSC JE. Right. Now, actually, he has given simply the devices, electronic devices, okay, and simple circuits using them. I am using the devices. But if you see the historical data of all available RRB JE papers, you can find the questions from different areas, different corners of the subject. That's why, if you see our self-paced program, RRB JE pre-recorded videos, I have given around 55 hours of content. Nearly 55 hours of content for basic electronics. Sir, why sir? Why? Because from the basic electronics, if you see electrical students, you can find at least 12 questions, 12 to 15 marks. And in fact, the basic electronics is given in the syllabus, but some questions are found from digital electronics also. That's why in the program, means self-paced program, I have separated the basic electronics into 2 parts, analog circuits and digital circuits. And if you go for the micro level subtopics analysis under analog electronics, you can find phase 1 semiconductor physics, phase 2 devices like diode, transistor, FET, phase 3 circuit analysis. Like that, I have separated the topics in a systematic order. And indeed, digital electronics is completely out of the syllabus for electricals in this paper. But if you see, some questions are found from the digital electronics. Surprisingly, sometimes the number of questions from digital electronics, maybe 1 or 2 years I have seen, number of questions from the digital electronics are more than that of analog electronics. But here the fortunate thing is, whatever the questions given from digital electronics, those questions are very easy, very basic fundamental level. The students having the basic idea, if they have touch with the fundamental level of digital electronics, they can answer them. So that's why I have added 12 to 13 hours of extra topic in self-paced program for digital electronics. So whatever the basic levels that questions are found, so those topics have been covered in that particular topic. Right, that's why. But here in this live, everyone who are watching the video should be benefited. So that's why I have selected the questions equally from EDC, like device theory, semiconductor physics, circuits means analog electronic circuits, and digital electronics also, right? So please do not ignore digital electronics. Even in some of the papers, the weightage is little less in digital electronics as compared to analog. You should give equal priority. So basic electronics, analog circuits, digital electronics, altogether you can expect 12 to 15 marks, right guys? Let us go for the problems. I will, as I said, I will go for the problematic part, previous year questions. Like I will select one question, I will try to cover some relevant information. Then you can feel that the entire subject is actually going to revise, okay? Instead of giving you the question and the direct answer. Semiconductors. I have selected the first subtopic from analog electronics, that is the semiconductors. With which of the following, the intrinsic semiconductor silicon be doped in order to obtain p-type semiconductor? You see, you try to read the question carefully. So the main important agenda of the student and the minimum the requirement of the student to prepare for this RRB JE is actually they should understand the terminology of that particular subject. Terminology is very important. And that too, if you are unable to understand the question, you try to read it multiple times. Because in RRB JE, SSC JE, and AP, TS and Maha Transco and Genco papers, if you verify, sometimes the questions intentionally, they don't give you the detailed view of the questions. Student has to understand the question carefully by reading it multiple times. But GATE and ESC questions are not like that. 100% information will be provided in the question itself. Okay. So he is asking the p-type material, dopant element, that's all. In order to get p-type material, we need to add what kind of dopant element, what kind of impurity, I am asking you, what kind of impurity. So we are adding the third group elements, like we call it as trivalent impurities. Fifth group element, we call it as pentavalent impurities to the fourth group element. Third group element, trivalent. Fifth group, pentavalent. In one of the paper, this question also given. What about the fourth group element? Like we have our silicon and germanium under fourth group elements, okay? Tetravalent. It's okay. That is the point you have to note down, okay? Right. In order to get the p-type material, we need to select a trivalent impurity. Trivalent means third group element as a impurity or dopant element. So what are the trivalent impurities are third group elements? You know, third group elements. Boron, aluminum, gallium, right? So these are the elements. So sometimes, luckily in this question we can find only boron. In some of the papers I have seen that third group elements, I'm just writing the names, like first letter boron, aluminum, gallium, and also indium. These are the elements. Examiner may give you boron, gallium, indium also. Then how to select? This is what the thing we have discussed in the class. Priority order must be like this. So by default, if you find boron, you have to select the boron. So we can select only one option, you know that. So that's why here we need to select option A. So I can give directly p-type semiconductor boron answer. I know the answer, I know, right? So directly I can select, but I want to give you some extra information. How many points we have obtained from this discussion? Fourth group element is also called as tetravalent, one of the important bit. And priority order, a new point maybe for some of you guys, right? Now, good evening. Kiran Kumar, good evening here. Notes, okay, I will try to provide my number here, otherwise email ID. So I will try to send it. Or otherwise, by tomorrow, I will try to find. I will try to ask our team. So our team can suggest me whether can I give the number or they will provide the notes through other channel. So accordingly, I will take that action, right? Gaurav, thank you dear. Thank you very much. Right, sir. Right, now coming to this question. To obtain the p-type semiconductor, just now we have discussed it, third group, right? Third group is also called as what? Trivalent impurity. Next, when donor type impurity is added to a semiconductor material. So, donor type impurity, you see guys, first of all, this is a key point you need to highlight. Impurity, okay, but we don't have donor type impurity, we can have trivalent and pentavalent. After adding them, that atom will becomes ion. It may be a positive ion or negative ion, donor ion or acceptor ion. So if you dope with a fifth group element, for example, right, it can have one excess electron. That electron will be released, of course, enters into new energy state. So then that atom will becomes we can say that whatever the atom we are adding, impurity atom, will becomes a positive ion. The positive ion is also called as donor ion. So the number of donor ions in unit volume wise, we calculate number of donor ions or positive ions are same. So number of positive ions are nothing but donor ions. And this is actually the story in a N-type semiconductor. Okay, right. So donor type impurities are added. Then what will happen, he is asking. Electrons will be generated. So donor is also called as positive ion. Positive ion can give you the equal amount of electrons, okay? Equal amount of electrons. So you also please keep on type the answer, so I think I can understand, right? Electrons are generated. Electrons are generating, it's okay, but then what about the type of material, China? Right, Kiran Kumar, obviously. Right, so that electrons are generating means it is a N-type semiconductor, no second thought. Sorry, so option A. The energy gap in semiconductors. So if you remember this particular topic, based on the easy value, materials are classified so and so, like that we have started in the lecture. Insulators, conductors and semiconductors. Conductors easy value nearly 0 and insulators 5 and above, but for semiconductors in between, but actually not exactly the center, of course. Its value around 1 to 1.11 electron volts. So based on that we need to select one of the option. It's okay. Semiconductors EG value around 1 electron, and not exactly 1 electron, okay? It is in the order of 1 electron volt. For germanium 0.78 electron volts. For silicon 1.1 electron volts at room temperature. Again, if at different temperatures, values are little different, like that, okay? So not only this answer, I am trying to cover that, recall the entire discussion of energy band diagram, how they classified based on the magnitude of EG in the simple way. How many electrons are there in the valency shell of a pure semiconductor? Obviously, for semiconductor means it is belongs to fourth group element. So group number of periodic table indicating what? number of electrons in its outermost orbital. So for fourth group element, we can have 4 electrons in its outermost orbital, right? So it may be, this question may be say number of electrons in the valency shell of pure, it may be semiconductor. Pure semiconductor means intrinsic semiconductor, okay? So next time they may give you the same question like intrinsic semiconductor, or maybe silicon, they can ask you, maybe silicon or germanium, maybe tin or maybe lead also belongs to the fourth group, okay, right? So see. In a p-type semiconductor, minority carriers, obviously in p-type semiconductor, majority carriers are the holes and minority carriers are the electrons. Okay, Kiran, you don't worry here, not only for this particular topic, okay? So entire subject, I will try to provide the notes, don't worry, right? In a p-type semiconductor, minority carriers are. P-type semiconductor, holes, electrons are the minority carriers. Holes are the majority carriers. At room temperature, current in intrinsic semiconductor. He is asking about intrinsic semiconductor due to. You know that in intrinsic semiconductors, we don't have a concept of majority and minority. N is equals to P is equals to Ni. Do you remember this? Ni is intrinsic concentration or intrinsic constant, and N number of electrons and P indicates number of holes or vacancies. In intrinsic semiconductor, always N is equals to P is equals to Ni. Ni is we are having some formula for that. Finally, I have concluded that Ni is proportional to T power 3 by 2. So the number of electron hole pairs in a unit volume of intrinsic semiconductors is a function of temperature. It's okay. Maybe room temperature or maybe above the room temperature also, the number of electron hole pairs remains constant. I mean, for example, at room temperature, we can have number of electrons 1.5 into 10 power 10 example for cubic centimeter. Beyond that, maybe pair value maybe increases at that particular temperature. If the temperature is fixed, this value also fixed. But the common point is, at any cost, electron hole pairs, or strictly speaking, number of electrons and number of holes, the quantity will be remains same. Okay, so obviously current is due to both electrons and holes. In n-type semiconductor, electrons majority, holes are minority. Okay, so that in n-type semiconductor, current is mainly due to electrons. In p-type, current is mainly due to holes, maybe due to both electrons and holes, but as comparatively, for just example, in n-type semiconductor, if electron concentration is in the order of 5 into or 10 into 10 to the power of 15 or 17, but hole concentration will be in the order of just hundreds to thousands. Okay, sometimes maybe 10 to the power of 2, 10 to the power of 3, that's all. Okay, so that's why in extrinsic semiconductors, we need to think about electrons or holes. Intrinsic, both. But in any material like maybe intrinsic or extrinsic semiconductor, current will never due to ions and atoms. There is no momentum in ions and atoms. Current is mainly due to either electrons or holes or maybe both. Okay, so as per the question, holes and electrons both will participate in the current conduction. At room temperature, a semiconductor material is actually a semiconductor material at room temperature. Indirectly, you should understand, he is not given n-type or p-type. This is RRB JE 2015 paper. So by default, we can take intrinsic. Same concept can help you to answer this question also. It cannot be like a completely dead. There are some, as the room temperature is available, there will be some conductivity. It may not be a very good conductor, okay? Slightly we can expect some conductivity, right? Slightly conducting. Which of the following has highest conductivity? Silver, aluminum, platinum and tin. Platinum and tin. Can you guess the answer? Actually the order is gold, next silver, aluminum, platinum and tin. Tin and then lead. Tin and lead, of course, almost same conductivity. In place of tin, you can find lead also, Pb. Tin, tin, he has given tin actually. They can give Pb and SB, lead also, right? Tin or lead both are having same conductivity. This is the order. This is the order, the conductivity, otherwise I will write like this, high and low. Highest conductivity. But practically, almost all materials are the good conductors, no doubt, okay? But comparison wise, gold is very good conductor compared to silver. Silver is having good conductivity compared to aluminum and so on. So as per the option, gold not provided, so that silver, okay? Arvind, yes, JE Prep, correct here. So please keep on type the options, okay? Don't worry whether your answer is correct or wrong. You just keep on involved, okay, in the concept. Try to recall without opening any notes and material. So that is actually the best way to recollect the data. If you find anything new data points here, better to take a notes on rough paper, better, just a short notes. You may be good in the subject already, okay, but you may get at least 1 point. If you could get at least 5 points in this 1 hour class, and if that out of the 5 points, at least if you see one question in paper, then you can simply very happy. So you will definitely benefit it, okay. So the most commonly used semiconductor, obviously silicon. There is no second thought, okay. Silicon is more abundant element. Not only that, as compared to germanium, semiconductor means we have silicon and germanium only. So that the more popular semiconductor is actually the most common semiconductor is silicon. So silicon atomic number is 14. Germanium atomic number, do you remember? 32. So as compared to germanium, in silicon, if I want to extract an electron, detach electron from outermost orbit, we need to apply more energy. That's why easy value of germanium 0.72 nearly, but for silicon 1.1, we need to apply more energy. Sir, you are saying applying more energy means it's a loss? No. That amount of energy is not easy to obtain very easily from the temperature variations or temperature what we call fluctuations. So that's why temperature insensitivity is more in silicon as compared to the germanium. That's why in electrical controllers also, like power electronics, we have SCR, silicon control rectifier. So in that high power devices also we are using maybe IGBT or maybe UJT, SCS, SUS, PUT, whatever may be in power electronic devices. We are using only silicon, no concept of germanium. Very rare cases, some of the electronic equipments we are using germanium. The reason is different. We'll discuss because of its mobility. That's a different story. But for stability wise, the best and more common element is silicon. The forbidden energy gap for germanium, just now I told you, na? Forbidden energy gap. Forbidden energy gap. The energy gap between valency band and conduction band, okay? Forbidden energy gap between these two, right? Valency and conduction band. Rough sketch of energy band diagrams. We don't have in-depth analysis of energy band diagram. Around 1.1 for silicon, 0.72 or 0.78 for germanium. So we don't have two options, we have only 0.72. So strictly speaking, 0.72 is a value at room temperature, 300 kelvins. Absolute temperature, 0 kelvins, we need 0.78 electron volts. Okay? Anyways, 0.72 is correct answer. The temperature coefficient of intrinsic semiconductor. Remember guys, intrinsic semiconductors and insulators the temperature coefficient is NTC. NTC stands for negative temperature coefficient. Intrinsic semiconductors and insulators exhibits negative temperature coefficient. Extrinsic semiconductors. Extrinsic semiconductors means our N-type and P-type semiconductors. Not only that, and conductors. Conductors exhibits PTC. PTC stands for positive temperature coefficient. Extrinsic semiconductors and conductors exhibits a positive temperature coefficient. Okay. So this is the point I can recall from this question. I am just utilizing the question to recall my data from randomly from the big subject. Okay. You try to do like that. Not only the question to straight answer during the preparation time. Intrinsic. Negative temperature. Just negative. He has given negative. 2015. Okay. Mobility of electrons is highest in. Actually, this is little contradictory question. Look at this, guys. Mobility in gallium arsenide, mobility of electrons in gallium arsenide, generally much greater than germanium. Okay. After that, silicon, comparatively, and then carbon. So highest mobility, gallium arsenide. Am I right or not? Immediately students will go and select it. No. Why? GAAS. Technically, it may be typing mistake or maybe intentionally examiner might provided that information. I don't know. But it is GAAS, okay? Actually GAAS, gallium arsenide. So that's why we should, safe side, we should go for the next priority element, that is the germanium. Luckily has given the mark for germanium only, right, sir? Mobility wise. This is the order you can take it. Mobility. Again, mobility of electrons and holes, do you remember? We have discussed this concept by taking the table, taking the average values. I have given that mobility of electron greater than hole by 2.5 times average value, right? So extra information in generally in any material. Mobility of electrons always greater than mobility of holes. Actually, as the live is streaming between my current time frame to your time frame, there will be around 20 to 25 seconds gap. If you type the option A, for example, some students are given the option A or B or C, something. That might not be for this. Maybe by this time, you people may be watching this question, I don't know. That's why so many students given B here. Okay, right. Okay, you please keep it in mind. If you want to ask the question, you need to type the question also. here. Then sometimes you better option D, someone is saying B. Better if it is possible, you are typing just option B na 0.72 also if you type. That is more convenient for me, because if you do any mistakes immediately, I should give you the reply. Okay, please keep it in mind, my dear friends. Kiran Kumar, Arvind. Only JE Prep 2025. Only these 4 guys, Balaji. And please keep on, type the answers. A body containing electrons, very interesting question. Less than its normal number. Electrons are less, it's okay. It is not about a N-type and P-type semiconductor. Some students are confusing. Of course, they are confused in this question between electrical neutrality topic and this one. According to the electrical neutrality, do you remember the charge of N-type or P-type semiconductor? If I show you N-type semiconductor, question also will be like that. Charge of N-type, no second thought, this is a question format. Charge of N-type semiconductor or charge of P-type semiconductor. What is the answer? Neutral or electrically neutral based on the option. Okay? But here, it is not about a completed or extrinsic or some solid semiconductor material. See, he is asking the question about a process. During the process, something he observed, and he is asking the question like a body, this is just a body or element or an atom. Body means it's an element or an atom, okay, containing electrons less. That means what? During the doping also you can see this kind of observation for that element, for that small body. Lack of electron charge negative, you know, lack of electron means positive. Lack of electron means positive. If the atom donate the electron, it will become donor. Electron charge negative, but donor charge positive, you know. Donor charge is positive. That's the reason. Lack of electron. In this ion, atom, if electrons are less than actual electrons, fifth group element, actual electrons 5 in outermost orbit, but one electron is donating. Okay? So whatever may be that chemical action, you forget about it. So donating. So now only 4 electrons are available. Actual electron means it is decided by its group number, fifth group element. Actual electrons 5. It has to be maintained 5 electrons in its outermost orbit. But there are 4 electrons, lack of 1 electron. 1 or 1 plus whatever, lack of electron. Less number of electrons means automatically it will become ion, positive ion. Okay? Right. So less number of electrons, right? That, yes, electrons. That's why positively charged. Positively charged. Be careful while solving these kind of questions. Read the statement carefully, each and every word, okay? Right. If a question is completely contradictory, no need to worry. That is not our, you no need to take that risk, okay? If question is completely contradictory, they will give the mark. But we should not do the mistakes. Movement of electron caused by application of electric field. This is a direct statement, you know. Do you remember this? Vd is equals to mu E. Anyone remember this? I have given this explanation in live class and offline class, online class, okay, recorded class. So I have given this explanation, equation explained for around 10 to 15 minutes to give the mobility, mu is a drift constant, mobility, we'll talk about the drift and diffusion. Mobility, units of mobility is a standard question in your paper, your exam, public sectors, okay, standard question. Meter square for volt second. What is it? Meter square for volt second is a unit for mobility. But what is this actually concept? Drift velocity. So the electron, the flow of electron under an electric field, okay, under an electric field is actually called as what? Drift current or diffusion current? Drift current. Diffusion current is different, and here mu is a drift constant. Diffusion current is different. Due to diffusion current, what is the reason? Important objective bit. What is the reason for the diffusion current? concentration gradient. This keyword is important. Concentration gradient is a reason for diffusion current. Drift current, electric field. Okay, right. Now you let me read this. A movement of electron which is caused by application of electric field. As it is, we have discussed it. Okay, electric field is actually drift current. Drift current. Diffusion current means due to concentration gradient. You should write it here. You will get 2 points. 3 objective bits. Mobility. So drift current is proportional to electric field. Mu is a proportionality constant. Mu means mobility or drift constant. Units meter square for volt second. Right? Question number. Good idea. Who is this? Kiran. Okay. I will write the question numbers here. Now onwards, I will write the question numbers. Now onwards. Thank you, Arvind. Very good. Arvind. Thank you. Super, you have given the direct answer. But I will, Kiran, I think, good suggestion. I will write the question number. But take it as very serious, okay? Your answer should be like 100% true. Like that you use the mind but do not open any books. Just casually you can read the question, and I am giving some time gap also. I am not moving question by question very immediately. My task is not questions, covering the number of questions, okay? My task is to give you some basic information, right? So for example, this is the question number 1, okay? Just now I started numbering. Current flow in a semiconductor due to, very nice question. Semiconductors. Do you remember it? I have given under the same topic 4 questions, 4 different questions. Drift current exists in, diffusion current exists in, 2 questions. Next, in conductors, what type of current exists? Semiconductors, what type of current exists? Like that I have given 4 questions, and this is one of the question. In semiconductors, you can find semiconductor devices means automatically semiconductor means devices, right? N type and P type. There is no device without PN junction. There may be strain gauge is not a device material, right? But there is no device. Maybe a LED, light emitting diode, laser diode, PUT, okay, IGBT, FET, MOSFET, JFET or any VFET, VMOS, transistor, whatever may be the semiconductor device. You can find the P type as well as N type. Carrier will flow from high concentration to low concentration. That kind of current is generally called as what? Diffusion current. So not only diffusion current, we are providing biasing. Due to the power supply potential difference, we can expect current, drift current. Which one is more is a different story. But which kind of current is passing through it is our main theme. In semiconductors, we can see both drift current as well as a diffusion current. But in conductors, there is no concentration gradient, no diffusion, only drift, okay? In conductors, only drift. So I have given 4 questions here, right? And semiconductors, both drift and diffusion. Drift current is correct, diffusion current is correct. There is no concept of displacement current, okay, in semiconductors. It is not like a space element or it is not like a capacitor or something else, just no concept of displacement current here. So that 1 and 3 only, okay? C is the correct option. Very good. Good, nice, very nice, man. Right. Let me go for the next question. Dash has the greatest mobility. Electrons, ions, no concept of mobility, okay? First of all, ion, no concept of mobility. Electron, hole, just now I have given maybe 3-4 slides before, okay? Electron is having more mobility. Question number 2. Very interesting, challenging, so that's why I will give you the time. In a p-type semiconductor, Fermi level, not only p-type, try to give me the answer for p-type N-type, P-type and N-type are extrinsic semiconductors. Even I want the answer for intrinsic. Same question, single answer, but I need 4 questions from this, 4 correct options, okay, regarding to this particular question. N and P type are extrinsic semiconductors, but intrinsic semiconductors also. This is valency band and conduction band, okay, VB and CB, right. I'm waiting for your reply. But this particular question number 3 is for P type semiconductor, Fermi level, Fermi or Fermi energy level, okay, which is near to valency band or conduction band or center. What are the options? Bottom of the valency band, top of the valency band, like that he has given. I think still you people did not see this question. There is a 25 seconds, 25 to 30 seconds late. Okay, so I'm waiting. Q3. Yes, Q3. Think. Okay. See, for P-type material, holes are the majority, you know that, okay? And for N-type material, electrons are the majority. But in intrinsic semiconductor, electron hole concentration is same. That is a hint I can give you. At least one answer enough. I can happily go for the answers for 3 different. I can give 3 questions. Single question okay, but at least if I see one correct answer, I can give you 3 model questions from this area. Q3, who is this? D. Kiran. Q3 na? Yeah. Still. Kiran, top of the CB or VB? Please verify it. For P-type material, intrinsic semiconductor I am giving you, okay, like this, center of the energy band diagram, exactly at the center of the energy band diagram. N-type semiconductor here. Do you remember this? N-type semiconductor. So, last one, the leftover, you can guess it here. P-type semiconductor, right? Top of the, what are the options? Top of the conduction band, bottom of the conduction band, top of the valency band. Top of the valency band. Top of the valency band, bottom of the valency band also given. Top of the valency band. Kiran, is it clear or not, China? Kiran? Yeah. This is valency band, this is conduction band. Holes near to valency, electrons near to conduction. If it is intrinsic semiconductors, center of the energy band diagram. Center of the energy band diagram. No problem. There is a chance of getting confusion, no need to worry. But you should understand where you are. Okay. So in this area I need to revise the notes. At least we should get that idea. Okay. Right. You take the notes. I'm going for the next question. Kiran, okay. JE prep. Yeah, it's common, Kiran. It's common here. See, trick means actually we don't have shortcuts for semiconductors. But I can tell you one thing here. See, this is an atom, China. Look at this. Just it is like a shortcut, okay? Don't be very serious. Practically we cannot prove it. Either we can explain through pure semiconductor physics concept, but here I can't explain the complete concept. Simple. For example, Here in this atom we have some electrons, you just assume like this. Whenever the covalent bond structure is broken, okay, electron will release na, like this. So electron will enters into conduction band only. Once if electron is released, it will enters into conduction band, okay, that's all. That is enough. This is only the way I have explained, apart from the derivations and mathematical equations, final conclusions in simple language, very simple terminology. So electron energy always in the near to conduction, that's all. For n type, lack of electron is nothing but what? Vacancy in a hole. Hole is an element belongs to valency. It is not true, it is a shortcut, simple, okay. That's why hole means p type. So for p type, energy band, Fermi energy will be near to the valency band. For n type, Fermi energy will be near to the conduction band. Like that you understand, okay. Now is it okay? JE Prip and Kiran Kumar. Is it okay? Shall I go for next question? Right. Okay, let me go for the next question. The process by which impurities are added. I don't want to waste time here. Doping, okay? Doping. Impurities mixing means it is a doping. Yeah, these are the some selected questions, okay, from the semiconductors. Now the devices. Which of the IV characteristics, okay, represents a PN diode? You know PN diode VI characteristics. Up to cut-in voltage, ideal case, okay, practical case, up to cut-in voltage there is no current, then current will start like this. But in the reverse bias, up to some extent almost current zero, okay. Suddenly avalanche breakdown will take place, okay. So which option is suitable for this? Which option is suitable? C. And options are very near to each other, don't worry about it, okay. It is just at a, it is not exact paper, okay. So no problem, in the main paper if you see, you can find some difference. It is exactly passed through the origin here also, almost like a tan wave, okay. But this is actually up to certain value, current very less, almost zero, then slightly increases. But here abrupt change, avalanche breakdown, you can easily recognize it. MOSFET in our syllabus. No, Kiran, actually FET, very intelligent guy, this guy, very intelligent guy who made this syllabus. He has given just FET. FET means JFET and MOSFET, both will covered. But in our lecture also I have covered all theoretical information of MOSFET, especially EMOS, okay, enhancement MOS. Basic questions only. They don't ask you FET, MOSFET biasing, MOSFET amplifiers, nothing. Whatever the common points we have between JFET and MOSFET, VVR, voltage variable resistor, which region, okay, or what is the meaning of saturation point. That basic current equations, maybe only once or twice a current equation related question is found. Majority of the cases theory questions. Let me tell you one question, repeated more than 20 times, one question, that is FET is a, or JFET is a, or MOSFET is a. Questions answer is same, voltage control current source. This is quite common question, okay. We have discussed these things again in here also. I will try to discuss, I will try to take that question, okay. Good question here, because we should have clarity in syllabus, na. For PN diode, PN junction, when N side is more positive than P side, N side should be more negative, na. So it is reverse bias. So forward bias is wrong. Reverse bias, large, small current, reverse bias, but current is I naught, nano amperes, leakage current, okay. That's why in that aspect he made this question. Reverse bias and small currents exist. Xeno diode is a reverse biased diode. We always use a Zener diode in reverse bias, okay. This is the symbol of Zener diode. Unregulated voltage we are providing here, okay, unregulated voltage. Strictly speaking, we should give like this, okay, some unregulated voltage, positive and negative terminals, right. And this is the regulated voltage we can obtain at the load. Output voltage is nothing but Vz. Zener diode should conduct, okay, in this direction. Properly we should provide the, select the resistors and all. And voltage across the Zener diode Vz is actually the output voltage. It is, its value is constant, remains constant under practical ideal conditions. Practically a slight variation due to internal resistance. So finally conclusion, Zener diode is a reverse bias device. PN diode, okay, PN diode, LED, light emitting diode, these are the forward bias diodes, right. Tunnel diode. Here in tunnel diode, do you remember or not, we are using very high doping. Doping profile, while explaining doping profile, I have given that. Extremely heavily doping is preferred in tunnel diode. The doping profile value is around 1 is to 10 to the power of 3. Okay, for every 10 to the power of 3 silicon atoms, there will be one dopant atom. Extremely heavily doping concept, or extremely heavily, or heavily, very heavily doping, both are same. Extremely heavily or very heavily doping profile is preferred for tunnel diode. Yes, tunnel diode. So tunnel diode is a special diode in which only in the tunnel diode we can have a special property called negative resistance. You can add this point, negative resistance property we can see in the tunnel diode. It is a high frequency. It is actually it is not a normal diode like heavily doping. Because of heavily doping, actually the switching speed of this tunnel diode is very high. The main specification is due to the negative resistance property, we are using it for microwave frequency oscillators, okay. So high frequency oscillations or picosecond pulse train, picosecond pulse train implementation also we are using tunnel diode. So because it is a high frequency device, that's all. These are the extra points we can take. And for the question, what is the answer finally? High resistivity, slow amplifier, no, very high doping, that's it. D is a correct answer, reasonable answer, okay. A PN junction diode's dynamic conductance is directly proportional to. Okay, you type this answer, okay. Dynamic resistance, you know, it's already 8 o'clock. We'll continue the session in tomorrow's class, right. Tomorrow evening also, immediately no introduction and nothing, directly I will start the session with problems only. Meanwhile, you type the answer. So dynamic conductance, not the resistance. But what we have discussed, the dynamic resistance. Do you remember? RD equals to dynamic resistance or AC resistance of the diode is equals to RD, eta Vt by IF. But the question is about conductance. Discussion. We made the discussion for resistance, dynamic resistance. This is dynamic conductance. 80% of answer I have given already, okay. You type the answer. Tomorrow, in the tomorrow session, I will again start with this. I have given 80% of the answer. We have discussed RD equal to eta Vt by IF, dynamic resistance. This is the question for dynamic conductance, and you look at the options. Okay, okay guys, we'll continue in the next session.